Sorry. Perfect.
Testing, testing. I'm not sure I hear myself. There I am.
Do you want to hear yourself a little bit more?
No, that's okay. As long as it...
Yeah.
So welcome back to Sources of Parallelism and Locality. We're in the middle of a two-part lecture, and so let me just move on ahead to the slide I want to be on, which is a review of where we were last time. So the whole point here is to say there's certain patterns that come up over and over again, so they're solved problems, and you don't have to solve them every time you see them, about how to recognize that given something you want to simulate, there's easy to find the parallelism and it's easy to find the locality, so you can minimize how much the processors have to talk to one another. So last time we did discrete event systems where everything was discrete, the time was discrete, space was discrete, or the number of states were discrete. And we have three more examples we're going to do today, which get ever more continuous. So I'm going to add a level of continuity each time, and some of the techniques that we used in discrete events will appear again, but there'll be some new ideas that come up. So the three next ones are going to be particle systems, lumped variables, and continuous variables, where everything is continuous. That's another word for partial differential equations. But just to remind you what we did about discrete events, that's sort of like the game of life or digital circuits or Pac-Man, games like that. So finite set of variables, they only have values at a finite discrete set of times. And there's a transition function which takes the value at the last time, computes something, and gives you the value at the next time. And so to find the parallelism, there sort of was a natural domain decomposition. The simplest example I gave was the game of life, so you have a square array, so you can assign a subsquare to every processor. And that's the simplest way to do it. But remember, our goals are to balance the load and to minimize communication. So what if you have something more complicated than you're talking to your four nearest neighbors, north, south, east, and west? What we did was we said, well, represent each object in your discrete event system by a vertex or a node in a graph, and have an edge going to all the other vertices on whom it depends. So if you have a real digital circuit, right, each of those vertices represents something in your digital circuit, an AND gate or a flip-flop, and the edges are actually the wires that go off and depend on other things. And so what we need to do is take that graph and partition it among P processors so that every processor has about n over P vertices, so that makes it load balanced. And so the number of edges that go from one processor to another, that represents data that has to move, those are as few as possible. We call that the graph partitioning problem. We'll see it over and over again. And as I said, it's NP hard to solve it for real, and so there's a lot of work in approximating it. And we will talk about those tools in a later lecture, but we'll see the need for that graph partitioning problem in all the other things I'm about to talk about, like lumped variables. And then there were two kinds of ways to simulate it. You could either do it synchronously, go time step by time step, or you could do it asynchronously, where you waited until an event came in before you made a change. And there were two ways to do that. Conservative, where you don't go any farther ahead than you know the right answer. Trouble is we had deadlocks to deal with. And the other one was just to be speculative and simulate on ahead several time steps. The danger there is you may go too far and have to back up. So either, there's no one best scheme, but that's a quick review. So are there any questions about discrete events before we go on to particle systems? Okay. So now a particle system is still discrete in the sense it has a finite number of particles, but now they all have a continuous position, x, y, z, or x, y, and they're all moving according to, say, Newton's laws, F equals ma. So if you can figure out what the force on them is, what F is, you divide by m, you get their acceleration, and you can move them. And time is continuous. So we're going to have to, in the computer, only compute their positions at discrete time steps, and we'll have to figure out what those are. So here's a whole bunch of examples. So stars in space moving under gravity, or an electron beam where you have electrostatic forces pushing the particles around, and that's in semiconductor manufacturing. Or if you're doing molecular dynamics, you'll have atoms moving around, again, with electrostatic forces on them. Now, if you have neutrons, they're bouncing off of things, no electrostatic forces anymore, but it's still a particle simulation. And if you have cars on a freeway, you can simulate that the same way, but it's not, the interactions are a little bit more complicated because you have to have a model of the human and the car in there, but there's still particles moving around. And then balls in a pinball game again. And so many simulations are going to combine techniques from one system or another. And let me mention, since I see someone taking a picture, that there was a student request to put the PDF on the website. So there's both PDF and PowerPoint there now. So hopefully it's visible into whatever format you have. But you're welcome to take pictures if you like. OK, so the idea is that if I can compute the force in a particle, all the particles are independent. I can figure out how to move them. So the interesting part is, how do I parallelize the force calculation? And it turns out there's 3 different kinds of forces, and they're parallelized in 3 different standard ways. So the force in each particle is a sum of 3 different kinds. There's the external force, the nearby force, and the far field force. So the external force means it only depends on where you are. It doesn't depend on where any of the other particles are. So if you're a fish in the ocean, it depends on the current where you happen to be. Or if you have an externally imposed electric field, an electron beam, then you just know where you are, and you know what the potential there is, and you can figure out what to do. So in that case, it's embarrassing parallelism, right? It doesn't matter where the particles are. All they have to do, it doesn't matter to which processors they're assigned. They just have to know their coordinates. A little bit harder is going to be nearby forces, where you only depend on the nearest neighbors. And in the case of sharks and fish, the sharks are attracted to nearby fish, and they don't care so much about fish that are far away. Balls in a billiard table, it's only when they get really close and they collide that there's actually an interaction, and there's a force on them that you have to deal with. And in physics, there's something called a van der Waals force. And that is something about how dipoles interact with one another. And that decreases roughly as 1 over r to the 6th. So remember, electrostatics and gravity, that's an inverse square law. That's 1 over r squared. 1 over r to the 6th goes down so fast, people basically ignore it once r gets big enough. So that's also a nearby force. And that's been in science a lot recently, because that's people think how gecko feet work, among other things. Remember, geckos are these lizards that can walk upside down in the ceiling and just stick to whatever they want. And they think it's the van der Waals forces between their feet and the ceiling that does that. So that's going to be a little bit harder to parallelize. And the hardest thing of all is going to be the far field force, where everybody depends on everybody. So if you have like gravity or electrostatics, then every particle depends on everybody else. And we're going to have to figure out a more clever way to do that, because the obvious way, if everybody depends on everybody else, it's n squared work and global communication to figure out what the forces are. We're going to do a whole lot better. There's some amazingly clever algorithms that people have invented to solve that problem much better. And it's going to generalize beyond inverse square laws, because a lot of these forces are more generally governed by something called elliptic partial differential equations. So gravity and electrostatics, that's called Poisson's equation, but these techniques apply to much more general things. So we'll see them again when we talk about PDEs. So let me go back to the easy case, to external forces, and show you the solution in 1 page of MATLAB. So this is sort of the simplest way, data parallel code that you could write. And so I'm going to have an array of the initial fish positions. And so fish P1 is the first position, fish P2 is the second. And that's a single complex number, the xy coordinates, real and imaginary parts. I also have the array of fish velocities, similarly 1 through the number of fish. Array of fish masses. I want to simulate it from time 0 up to the final time. And the algorithm is going to be the simplest possible numerical method, which is also totally physically intuitive. I'm just going to say, if I know my velocity right now, I'll just move in a straight line with that velocity for a little time step. And if I know my acceleration right now, I will just move my velocity in that direction for a little time step. That's called Euler's method, but it's the simplest possible thing. You move along a straight line. And so what I'm going to do is start with time t equals 0. And I'm going to start with a time step of 1/100th of a second, but I'm going to have to adjust that as the algorithm goes along. That's the only part that's not embarrassingly parallel. So I'm going to loop over all the time steps. So while the time is less than the final time, I'll increment my time step. Each fish, so this is a line of parallel code. It's data parallel. I'll take my fish velocities, multiply by the time step, and add it to my array of fish positions to get the new fish positions. Then, depending on where I am, I will evaluate the current. Where I am in the ocean, I'll get the current there. That's embarrassingly parallel. And then I divide by the masses, component by component in MATLAB notation, and that gives me the acceleration. And I similarly update component by component the array of fish velocities by multiplying by dt times the acceleration. So that's as simple as possible, but I do need to do one thing that's not embarrassingly parallel, and that's update the time step, because I want to adjust it so that it's large enough to, so they don't take forever, but I don't want it to get too big that I get an inaccurate answer, and I don't want to make it too small, it'll take too long. So here's sort of a cartoon of what people usually do. I want to pick the time step so that no velocity changes by more than about 10%. So I'm willing to change the velocity at each time step by about 10%. So what do? I take the absolute value of all the velocities and take the max. That's communication. That's a reduction operation. So I compute the maximum fish velocity divided by the maximum fish acceleration, multiplied by 0.1, and that gives me a reasonable time step. I mean, fancy numerical methods are more complicated, but they all have this pattern of how you parallelize them, so this is really all you need to know for the parallelization point of view. And so you can think of this in using the language of MapReduce, which Google made popular. So what's the map? It's apply a function to every component of your vector. So multiply every component of the vector by dt and add these two vectors. And the reduce is the operation where you compute some function of a whole array of data. So the max of the absolute values of this array of data. So those are standard patterns that appear over and over again. Okay, so are there any questions about that really simple code? We'll do more complicated stuff later. So in the external forces, these are the simplest. The force in each particle is independent. It's embarrassingly parallel. So I can distribute the particles any way I like, as long as each processor gets one piece of all the particles. Then I'm guaranteed to have load balance, and locality is not an issue because I'm not interacting with nearby particles in any sense. Okay, so let's go on to nearby forces. And so now I do have to talk to my nearest neighbors, and there's going to be some communication. And the easiest example to think of is colliding billiard balls, which is going to be your homework assignment after the next homework assignment. And so the simplest algorithm is you look at every pair of billiard balls and you ask, are you close enough together to collide? That's clearly an n squared amount of work, and that's kind of a dumb way to do it. We're not going to do it that way. So what we're going to do is I'm going to use a technique that I introduced in the discrete event simulation. I'm going to use domain decomposition. So let's suppose this square is the physical domain in which all of my billiard balls are living. And let's suppose that I have 25 processors, and I'm going to arrange the processors in this 5 by 5 grid so that each processor owns all the particles that happen to be inside its domain. And so now, if I'm lucky enough that all the particles are evenly distributed, here they're not quite evenly distributed, but they're not too bad, then every processor will have about n over p particles to work on. Okay. So that's going to be my simplest load balancing technique. I'll have to make it better in a moment, but let's assume they're uniformly distributed. How do I deal with the communication? So I'm going to take advantage of the fact that since it's only nearest neighbor interactions, the only chance of having an interaction is when two particles are both very close to a boundary. So what I'm going to do is define these little blue areas near the boundary, the ghost zones. I think I called them that before. And the only communication that's required is when a particle is in this blue boundary in this blue zone near the boundary. Because if I'm in the middle in the white zone, my nearest neighbors can't possibly be on another processor. I own all the data. I can do all that in an embarrassingly parallel fashion. It's only when I'm here that I have to send that information to my neighboring processor so they can figure out in the next time step if something could go wrong. And there's a case where I have a possible collision. So here we ask the question of, okay, what is the right shape of these regions so that I can minimize the number of processors that are the number of particles that are likely to have to be communicated with my neighbors. And it's the same intuition that we had when we talked about discrete events. I want to minimize the surface to volume ratio. I want to have as little boundary region as possible compared to the volume, the area inside there. And in this case, in a nice simple square domain, I'm going to pick squares. And in 3D, I would pick cubes. But all of that's kind of assuming that things are evenly distributed. So what if they're not? So what I need to do is deal with load balance if the particles cluster. And indeed, most interesting problems, they do cluster. So here's the idea. I'm going to use a divide and conquer idea called a quad tree. So here's a picture of the data structure in 2 dimensions. So all the particles initially live in this big square. I'll divide it into 4 subsquares by drawing those 2 lines, and I'll assign all the processors to those 4 subsquares, and I'll ask, is that balanced? So here there are only 2. One processor can deal with that. There are only 2. One processor is good enough. But these 2 squares are both highly populated, so I have to do it again. So I'll take that subsquare and divide it again into 4 subsquares. That box is empty. I don't need any processor assigned to that to do any work. There, one processor is good enough for those 3, one processor for those 2. That's still pretty crowded, so I just keep on doing it recursively until I get down to all the boxes have some minimum number of particles in them, like 2 or 3 in this case. And so this is called a quad tree because I'm dividing it into 4 in 2 dimensions, and I won't try to draw the picture, but in 3 dimensions it's the same idea. I would take a cube and divide it into 8 subcubes, and so that would be an octatree. And so now it's going to be load balanced by design. Every particle, every processor is going to have roughly an equal number of every processor is going to have roughly an equal number of particles in it, and some regions may be unassigned, no work done there. And it's still roughly minimizing the surface to volume ratio because I'm still using these squares, so hopefully I will communicate as little as possible. Okay. Now, you may say, well, this is good. I do that once at the beginning. The particles are moving, aren't they? So what happens after a bunch of time steps and all the particles are being attracted, say gravity, and they're all sitting down there? Well, I have to repeat this occasionally. And depending on your problem, hopefully you won't have to repeat it very often, but you may have to readjust things. But in the meantime, when this particle moves and crosses the boundary, he'll be reassigned to that box. So you have to keep track over time of how imbalanced the load gets and occasionally rebuild this. So that's nearby forces. And finally, if there are no questions, we get to the really hard case where everybody depends on everybody, which are far field forces. And inverse square laws, gravity, protein folding, all of that, those are the canonical examples, but they don't have to be inverse square. And the simplest example, if you just write it down, is n squared. You take every pair of particles, compute the forces on one and the other, and add them all up. And so now, just decomposing space evenly is not going to eliminate any communication, because everybody has to be everywhere. So let's do the simplest possible algorithm and just ask ourselves how much it communicates. So what I'm going to do, suppose I have n particles and p equals 5 processors. I'll just assign n over 5 to each. Let me think of the processors as all connected in a loop like that. So what am I going to do? I'm going to take my n over 5 particles and compute all possible joint interactions. So I'll do n over 5 squared, roughly, interactions. Then I take a copy of my particles and send them to my neighbor. And every processor does the same thing. It sends a copy of your locally owned particles to your neighbor. Now I have 2 other sets of n over 5 particles, and I compute all of their n over 5 squared interactions. Then I send the copy to the neighbor, send the copy to the neighbor, and by the time I've sent the copy to the neighbor 5 times, every particle has visited every processor, and everything is fine. I've gotten the answer. So how much communication did I do? Every chunk of n over p particles has to move p times. So it visits everybody, and n over p times p is n. So this guy is going to move n, and that's kind of expensive. It turns out that there's a more clever algorithm that does exactly what I described, but instead of moving n particles, it moves n divided by the square root of p particles. So you can think for a moment how that might be possible. It's not obvious. We'll talk about that in a later lecture. But there's even a more clever algorithm where you don't have to do n squared work, where you can do order n work, and also a lot less communication. So let me give you 2 examples of these clever algorithms that do order n work. I'm just going to give you a kind of a cartoon of them because we'll have a whole lecture on them later because it is kind of complicated. So this is just sort of an overview. So there are 2 techniques to do it in order n, or let's say n log n. And they both involve approximations. We're not going to get the exact right answer. And so the first method for doing these far field forces are called particle mesh methods. And the approximation is as following. So here, suppose all my particles are living in a grid. Here's the physical domain. And now let me superimpose this square mesh on it. So these aren't processors. This is just a geometric mesh. So what I'm going to do is take all the particles and move them to the nearest mesh point. So I've drawn all these little arrows. So the first step of the algorithm says take all my particles and move them so they just live on these regularly spaced mesh points. If that's going to change the answer, that's an approximation. Now it turns out that once the particles live on this regular mesh, it turns out there's a different algorithm. because it turns out that the solution of the forces solves a particular differential equation called Poisson's equation, and there are algorithms based on the fast Fourier transform and multigrid that do it in order n log n or order n. That's not obvious. I'm just trying to give you a tour of what we're going to talk about those algorithms later. And then what you do is you compute the forces for all the particles just located at those mesh points. So what do I do with that information? Well, if I look at that guy and I know the forces there, and there at those four corners, I just average them appropriately to get the force right at that point. So I do this sort of geometric averaging with the neighbors. So there's three steps. I scatter the points. That's a scatter operation. Move them to the grid points. I solve the problem on the mesh by doing a fast Fourier transform or multigrid. And then I gather the information from nearby points to do the averaging. And so that's a good idea. But there's an even better way to do it. So, because this makes a pretty coarse approximation, which may be good enough in some cases. So this next one, you get to choose the approximation, and it's much, much cheaper. You can get as many digits as you like without an enormous cost. And so it's based on an approximation I think I've referred to before. Imagine you want to compute the gravity on a force on Earth. So you walk out at night and you look up in the sky and you see all these little white dots and you say, I have a lot of terms in my sum, don't I? And then you realize that one of those little white dots is the Andromeda galaxy. And it has a few billion more little white dots inside of it. And you say, I'm in trouble. But no, the Andromeda galaxy, your first impression was right, it's a little white dot. You can approximate it by center of mass, a single point. And in turn, the Milky Way looks like a white dot to the Andromeda galaxy. But once you're inside the Milky Way, each solar system looks like a white dot. You can apply this idea recursively at all levels of distance. And if you do that recursively, the complexity goes from n squared to order n, or n log n. And this was such a clever idea. It got its two inventors into 3 national academies, so it's had a big impact on many fields. And it's been the first idea approximately was called Barnes Hut. Then the best version of it was called the fast multipole method by Greengard and Rocklin. And so we will again have a lecture on the details of this later. So let me sum. So that's the end of particle methods, high-level tour. So here's a summary. The model contains discrete entities, namely particles, but now time is continuous and the positions of the particles are continuous. And it all comes down to realizing the force has 3 components: external, embarrassingly parallel; nearby force, just depends on the nearest neighbors; and the far field force, where you have to be clever to avoid spending order n squared time. And the 2 clever ways to do it are particle mesh methods, put all the particles on a regular mesh, and these tree-based algorithms, where you approximate the Andromeda galaxy by a little white dot. And so that's the end of particle methods. I mean, obviously we'll return to some of these later. But are there any questions before I go on to the next flavor, which is a lumped system, which is a generalization of this? Okay. So this is going to be one more sort of flavor of a mixed continuous discrete system, and sometimes you can call them systems of ordinary differential equations, but they're actually more general than that. And so I'm going to have a discrete set of variables, call them lumped. They don't have to be positions anymore. And each one depends on a continuous parameter, usually time, and some subset of all the other lumped parameters. Okay? So probably just a small subset of them, not all of them. And the canonical example could be a circuit. And I'm going to approximate that circuit as a graph. The wires are going to be the edges. And the nodes are going to be connections where 2 or 3 or more wires come together. And each edge is going to have some interesting property. It might have a resistor or a capacitor or some other electrical thing on it. So why do I call this a lumped system? Because when you solve and ask, what is the circuit doing, you don't want to know the voltage or the current at every point along a wire. You just want to know it at a few discrete points, where the wires come together. And so what I'm going to do is write down a list of those variables. What are the voltages and currents, at each point where all the wires come together. And I'm going to write down some equations. And in this case, the physical laws that govern them all are called Ohm's laws and Kirchhoff's laws. If we were a mechanical engineer, we'd have F equals ma, and Hooke's law. I'll show you an example later. But different physics gives you different equations, but it still looks like this kind of thing. And so you get a system then, since there's some derivatives in it, they're ordinary differential equations. But you don't always get just differential equations. So for example, one of the Kirchhoff's laws, I'll write it down in the next slide in more detail. It just says, electrons are conserved. What flows in has to flow out. There's no derivative there. It's just a sum equals 0. And so you get some algebraic equations too. And so altogether you get some differential equations and some algebraic equations, and the whole system is called a DAE, differential algebraic equation. So let me just write it down and tell you what the important properties are at a high level for the case of a circuit. And I'll do a mechanical engineering example after that. So here is my finite list of variables I'm going to keep track of. I'm going to have the voltages as a function of time at each node in the graph. I'm going to have the branch currents, so that's how much electricity is flowing from this node to that node if they're connected by a wire. And then one other thing is the branch voltages, which is just the difference between the voltage at one end and the other end of a wire. And so what equations do these things satisfy? I'm going to write down all of it in one sort of linear looking equation. So there's my vector of unknown values, all of these guys, multiplied by this matrix equals that vector. So it looks like a system of linear equations, but there's some derivatives in that matrix, so it really is a differential equation. And so let me just write down the 5 simplest laws of physics or of electrical engineering that fill up the matrix. And the first row is called Kirchhoff's current law. That just says that all the electrons that flow into, an intersection of wires have to flow out again. And so I'm going to encode all of that by this big sparse matrix A. So this first thing says that A times the currents equals 0. So what is A? It just is a matrix which is almost all zeros, but there's some plus ones and minus ones in it that says who's connected to whom. And so there's going to be one column in this matrix per branch or per edge, per wire if you like. And there's going to be one row per node where the wires come together. And there's going to be a plus one and a minus one in it. And so what doing this matrix times that vector multiply does, it basically adds up all of the stuff that goes into one particular vertex, and it says it's got to come out to 0. It's just conservation of electrons. So the next row is Kirchhoff's voltage law, and that simply says that the voltage from one end to another, just subtract them. So that's the transpose of the matrix I just defined times the node voltages has to equal the branch voltages, and there may be some sources, maybe some batteries in there, so that gets stuck in that. Then there's Ohm's law. Resistance times current is voltage. And now finally, I haven't had any derivatives yet. I finally get derivatives because it is a differential equation. So now it turns out that the current depends on the derivative of the voltage. And there's a sparse matrix there which has all the capacitances in it, wherever they happen to be. And there's also inductance. So this is the kind of thing that I'm going to need to solve. And the thing to take away from this is a large sparse matrix. So we're going to have to do a bunch of sparse linear algebra to make this thing run in parallel and be clever about it. So that's the circuit example. Let me just show you another example, which is structural analysis. And so, because there's a big project at Berkeley, which has a parallel piece of parallel software called the OpenSeas project to see what the response to earthquakes are of important things that we drive on every day. In fact, I believe this is the part of 880 that collapsed in the Loma Prieta earthquake. And so the question in retrospect is, how should they have built it so that it wouldn't have collapsed? But every time you build a building, you're required to do these kinds of simulations to do your best job at making sure it doesn't. So now, what are the variables? They're not currents anymore. They're the displacements. So at a whole bunch of individual points in the building, at the end of every girder, you have its position. And that's x, y, z coordinates. So what are the rules that govern how they interact with one another? Well, it's Newton's laws, F equals ma, but also Hooke's laws, which is just the spring constant, right? If something moves, then what's the force? It's proportional to the spring constant times the displacement. So you write down all those laws for everybody connected to everybody else. And so what are the 3 questions you could ask once you write down all those laws? The simplest one is called static modeling. You exert a particular force and you ask, how far does everything move? That's just solving a big sparse system of linear equations. You could also ask, more interestingly, the ground is moving, it's shaking, so you apply a continuous force and you ask what happens to the building. So there's your ordinary differential equation. And finally, you have an eigenvalue problem, a different linear algebra problem. So when you build a building, how are you going to be sure that no matter how the earth is shaking, because it can move in different ways, that it won't fall down? Well, what you do is you ask, what frequencies does the building like to shake at? What are its resonant frequencies? So, does it like, because, a resonant frequency is like of a piano string is the sound it makes. It likes to vibrate at that string. So what you do is you compute the frequencies, the resonant modes at which the building likes to shake, and then you look at historical earthquake data and you ask, at what frequency does the earth like to shake? And if those match, well, you're in trouble. So, because the building will go into resonance. So that's yet another analysis that people do. So now, let me give you one more example, which is used by people around the world, whether they know it or not. Star Wars. the force unleashed. Okay. So let me, actually, do I have sound here? I think, let me ask the folks in the back, how do I get sound? Because we certainly want to hear this. Okay. Let me, I should have connected this before, sorry.
While Jim gets set up, we can just have a
Yes.
few logistics comments.
Good idea.
So there's a few of you that did not turn in homework 0. If you're registered for the course for credit, do so immediately, seeing that the due date was past Friday. Also, everybody should now be assigned teammates for homework 1. If you do not have a teammate and are registered for credit, please again contact us immediately and fill out the survey. And if anybody is thinking about dropping the course, and please inform your teammates also quickly so that we can reassign them to the correct teams. And also, if you have any more questions, feel free to contact me or Aditya.
So the idea here is that whenever Darth Vader smashes something, your game box does real-time parallel finite element simulation, so you can see exactly, so that it's being smashed as realistically as possible. And how's the sound? Okay. So this was developed here at Berkeley by James O'Brien. And so I'm going to just show you a few of the examples here as we move along. But I just want to move ahead and show you some of the models inside, because they have different models for different materials. Okay. So for example, there's one model for stone, which smashes in a particular way. And it also has to be a simulation to get the sound right. So you have to actually compute the vibrations, that are created as these things collide. So glass is a little bit different. I think we'll hear that in a moment. And okay. Let me see, another one. Okay. So metal is also a possibility that has yet different properties. It doesn't quite break as much as glass or stone. And you can even have quite a bit softer materials. Like plants. So, which maybe he can't destroy quite as easily, also I suppose he'll try. So let's take a look at what happens here. So it just sort of shakes around a little bit. It's rather, so okay. Okay, the bark flies off, but it's flying off correctly in the physics. Okay, that's a strong tree. Okay, so now let me move ahead to show you some of the low-level details of this lecture. All right. Let me move ahead and show you what's actually going on the inside of the simulation. All right. So there's the end of the wood. So now what I'm going to do is show you what's going on the inside here by showing you what the finite element mesh. So there's the mesh that's being used for the simulation inside the machine. And you can see that it can be used for wood or it can be used for brick, whatever you like. And if you don't like the physics of that particular brick, there's the mesh. You can actually change the physical properties. So we'll see that in a moment. So here's going to be a pull-down menu. You can change the Young's modulus, the Poisson ratio, the density of the material, and you could make it be whatever you like, right? It's all just the same kind of simulation, and it bounces around a bit. And so I'm not sure that's part of the public user interface, but it is there. Okay, very good. Any questions about Darth Vader? So now let me go back. Oops. So that was playing on a Sony game station which had 8-way parallelism. And of course, it runs on many other platforms as well. Okay, and there you can download it and watch it yourself at your leisure. Okay, so in all of these examples, so circuits or mechanical engineering or games, the matrices are sparse. And so we're going to have some special data structures there because we don't want to store all those zeros, and we certainly don't want to compute in all of those zeros. And so let me tell you what the algorithms are so we know how we're going to deal with them in parallel. And so the two kinds of questions that we're going to ask when we have these ordinary differential equations are, I want to compute the values of the variables at some time, t, that's the obvious way to solve it. And there's two methods with two different ways of dealing with the sparse matrices, explicit methods and implicit methods, and I'll show you a cartoon of how they look in a moment. And then computing the modes of vibration, the eigenvalue problem. So let me give you a one-slide summary of what you need to know about the numerical method to see what the parallelization is like. So this is solving ODEs with explicit methods. I'm going to use the simplest possible ordinary differential equation. X prime is some function f of x. I'm just going to assume it's a nice big sparse matrix times x. Now, even if f is nonlinear, so that you can't write it this way, it's the same parallelization. All I care about is that you depend on relatively few of your neighbors, right? Because the physics limits the dependencies, and that means your matrix is sparse, because each non-zero entry is a physical dependence. And since it's a continuous problem, I can't solve that exactly. I need to discretize it. That means I'm only going to compute the solution at a bunch of discrete time steps. So dt, 2dt, 3dt. So I'm going to have this array of values, which I'm going to just use. So the square bracket is the index. So I'm going to compute it at I equals 0, 1, 2, 3. And so now, how do I do that? What the ordinary differential equation does is it basically gives me the slope of the solution. So here is the red solution. I know the solution at time t. I want the solution at time t plus dt. So what do I know? I know that how to compute the slope right there. So I know how to draw that blue line, which is going to roughly approximate the solution. So what do? I say that x sub I plus 1, the solution there, is going to be the solution there, plus, well, just move along the straight line with the slope. Where does the slope come from? Well, in the explicit method, I'm going to use the slope right there, because I know where I am, so I can compute the slope because x prime is the slope. And so just plugging that in, I get that x sub I plus 1, my approximation there, is going to be my x sub I, my approximation there, plus my sparse matrix times my vector times dt. So all the work comes down to doing this sparse matrix times a vector multiplication. And we will have a lot to say about how to parallelize those in the future, but right now I'm just saying this is going to come up a lot. And so so this is going to be relatively easy. I mean, we know how to parallelize sparse matrix vector multiply very well. There's a lot of good packages for it. Now the problem with this is, from a numerical point of view, is if you want to solve your differential equation this way, you can't take a very large time step. You can see here in this cartoon, the blue line and the red line are pretty far apart. If this red line were, let's say, really steep, like going up really fast, then I'd have a terrible approximation. The blue line would not do a very good job. Those kinds of differential equations come up all the time. They're called stiff. That's a fancy way of saying the red line can get very steep. So explicit methods don't always work. That's why I'm about to tell you about the alternative, which is an implicit method. And so now, instead of using the slope at that endpoint, I'm going to use the slope at that endpoint, at the other endpoint. So I'm still going to use the same array, x1, x2, x3, for the values at time 1, 2, 3. And I'm still going to use the fact that to get to here from there, it's going to be, follow a straight line with a particular slope. But now, as I said, I'm going to use the slope at the other endpoint. So how do I write that down? I'm going to get that so I'm going to say that the slope of this curve, that's x sub I plus 1 minus x sub I divided by dt. That's just the straight line. That slope is going to have to be a times x sub I plus 1. That's the slope at that endpoint. So now, what do? I know x sub I don't know x sub I plus 1, so I have to solve this equation for x sub I plus 1. When I do that, I don't have a nice closed form formula for it. I have a system of linear equations that I have to solve. That identity minus dt times a sparse matrix, that's a big sparse matrix, times my unknown values at the next time step equals my old time step. So at every time step, I have to solve a big sparse system of linear equations. That is a lot more expensive than doing a sparse matrix vector multiply. On the other hand, I can take, for some ODEs, I can take so much larger time steps, this is the only way to do it. So which one do you choose, explicit or implicit? Well, it depends on the properties of your ordinary differential equation. And I'm not going to talk about that in much more detail. I'm just going to use this to motivate. We have to do sparse matrix vector multiply in parallel, and I have to solve large sparse systems of linear equations in parallel. Okay, the last example that I wanted to motivate was finding the modes of vibration, eigensolvers. And so I just want to say where that comes from physically. So remember, my differential equation was x prime equals ax. So what's the mode of vibration? Well, it's x double prime equals ax. So just think of this as the acceleration equals, you know, the force divided by the mass. That's one way, or Hooke's law. You know, I've stretched the spring by a certain amount, and that tells me what the force is on a particular node. So how do I get the modes of vibration? I'm going to assume that there's some shape. X0 is a shape, which is the shape in which the building vibrates, and omega is going to be the frequency. So the building vibrates at this frequency, and that's called a mode shape. That's called the frequency. If I just plug this guy, x sub t, that form, into this differential equation, all the sine functions cancel, and I'm left with a plain old linear algebra problem. That this constant times that vector is this matrix times that vector. That's an eigenvalue problem. A is the matrix I started with, x naught, the mode shape, is the eigenvector, and minus omega squared is the eigenvalue, where omega is the frequency. And so what I need to do is solve this big sparse eigenvalue problem, and that'll tell me how the thing vibrates. And so a one-slide summary of where the time goes to do that. So for eigenvalue problems, I have to do something implicit. There's really no way around it. So there's direct methods, and those have the flavor of Gaussian elimination. And there's also iterative methods, which have the flavor of sparse matrix vector multiply. And so we're going to talk about these in the future, and there's going to be, you know, they're both going to come up. They're going to be direct methods and iterative methods. Okay. So having motivated sparse matrix vector multiply enough by now, let me go down one level and tell you what it looks like on the inside and how we're going to parallelize it. You know, not every level of detail, but a little bit. So here is a picture of a sparse matrix. All of the colored entries are the non-zeros. All the white entries are the zeros. So I don't want to store them or compute with them. And what do I want to do? I want to do y, that vector equals y plus a times x. Okay? So what is the most natural data structure to use, not the only one, to store this sparse matrix? I'm just going to store all the non-zero entries. So these 4 entries in those locations, the red ones, that's the first row, they get stored. Then the next 3 entries, they get stored. Then the next ones. So I just pack them all together, throw away the zeros. But if I've done that, I've forgotten where they're located. So I need one other array to remember what columns they live in. So this is column 1, 2, 5, and 9. So those 5 integers I'll store 1, 2, 5, and 9. And similarly, I'll do all those. But I still don't know where one row ends, the next row begins. So I need one more array to tell me where's the beginning of each row. So that points there, that one points there. And so I know how this row begins at that point, and it ends at that next value minus 1. And so that's going to be my data structure. So how am I going to implement then my matrix vector multiply kernel? I need to execute this little update here. This is the inner loop of matrix vector multiply, but I only want to do it when a is non-zero. Otherwise, it's not worth it. So here are the 3 lines of code. So for each row, I want to compute the dot product of that row of the matrix and the vector. And so I'm going to loop over all the non-zeros. So I'm going to loop from the beginning of the row to the end. So that's pointer sub I to pointer sub I plus 1 minus 1. So that loops over that array. And then I do the dot product. So I just go and get the values. Those are the non-zero matrix entries. And then I have to multiply them by the corresponding entries of x. But which entries of x? I have to look it up. This is going to be x1, x2, x5, and x9. And so I need to do this index right there is going to be looking up in that array, and those could be located, you know, anywhere in memory. So this is called indirect addressing, and that's going to be an expensive thing that we're going to want to optimize away if at all possible. Okay. So that's the simplest sequential algorithm. The question is, how am I going to parallelize it in a reasonable way? And so let me do sort of the most obvious thing first. And so there's my big sparse matrix. I haven't colored in every point. And let's suppose I have 4 processors, P1 through P4. So what are the questions that I need to answer? I have to decide, well, which processors are going to store the data? You know, who owns each entry of each vector and who owns each entry of the matrix? And who's going to be responsible for computing the dot product of each row? There's a whole bunch of ways to do it. The simplest way to do it is to say, well, I'm going to assign the first quarter of the rows to P1, the next quarter of the rows to P2, and that way, and everybody gets a copy of X, and then I just have to do all the local dot products, and I can compute the first, you know, n over 4 entries of Y, n over 4 entries, the next n over 4 entries of Y, and so forth. So that's not always going to be a good idea. So let me just be a little bit more general. So what I've done here is I've taken all the rows, that's an index set, I'm indexing the rows from 1 to n, and I need to partition them into P different groups to decide which processor is going to get which one. So processor 1 will get the indices in the subset n1 and so forth. And so what is processor K going to do? It's going to store, so processor 1 in this picture, it'll store all those entries of Y. It'll store the corresponding entries of X. I'm not going to copy X everywhere. I'm just going to have one copy to get started. So it's only going to store that much of X, and it'll store that whole row. Okay? And so then the question is, who's going to do the computing? Well, processor 1 is going to own that whole row of the matrix, so he's going to be responsible for doing the dot product and updating the entry of Y. But he doesn't have all the data he needs, right? He only has the first, in this picture, n over 4 entries of X. So there's going to be some communication required to share all the other entries of X with all the other processors. So let's just ask ourselves, what would the ideal matrix look like that wouldn't require very much communication, right? Ideally, there'd be, you know, very little communication. So here's the perfect matrix, and not all matrices look like this. So the question we're going to come back to is, how do I make my matrix look as much like this as possible? So if my matrix were block diagonal, if all the zeros, non-zeros, were only in those diagonal blocks, this would be an embarrassingly parallel problem. Each processor would own exactly what subset of X it needed, what subset of the matrix, and what subset of Y, and it would do a local matrix vector product, and I would be done. Okay? But of course, my matrix doesn't look like this. I have all of these other, you know, there's probably going to be a lot of non-zeros out there, so the question is, what am I going to do about that? And no surprise, it's going to turn into a graph partitioning problem once I'm done talking about it. So what's my goal here to assign work? I want to balance the load. So how do I measure the load? Well, how many floating point operations does a processor do? It's going to do 1 multiply and 1 add per non-zero in the matrix, right? So balancing, I have to balance the non-zeros. Each processor should get a roughly equal number of non-zeros. That's not the same thing as an equal number of rows, right? Because every row may have a different number of non-zeros, so I have to do that a little bit differently. I want to balance the memory, and you know, the memory is also proportional to the number of non-zeros, so these two are the same problem. I want to minimize communication. I don't want to send too much data around. So what I want to do then is, if my matrix doesn't look like this, I would like to arrange it, if possible, so that there are as few non-zeros out there as possible. Because every one of these non-zeros, if there's a non-zero there, I have to go get that entry of X from processor 3 to compute the dot product in processor 0. So ideally, my matrix, when I do the assignment, would have everybody would be close to the diagonal, and there wouldn't be anybody out there, or as few as possible. So, and then there's some local optimizations to it at the machine level, which I won't talk about right now. So the question is, how am I going to do this? I want to balance the load, and I want to minimize the communication. Well, that's going to be the graph partitioning problem. So let me now remind you of the graph partitioning problem, and I'm going to draw a matrix and a graph, and just make it clear that these are isomorphic. It's just talking about graphs and talking about sparse matrices are just two different languages for the exact same thing. So here is a very simple 6x6 sparse matrix. And here I've represented it as a graph with one vertex for every row and column, so numbered 1 through 6. And for every non-zero, besides the diagonal ones, I have an edge in the graph. So here I have an edge connecting vertices. You know, here the entry 1, the 1, 4 entry of the matrix is non-zero. It's that green one. And so I have an edge from 1 to 4. That's the green one. There I have a non-zero going from 1 to 5. And so I have an edge from 1 to 5, and I've colored it purple. And this is a symmetric matrix, so if 1, 4 is non-zero, so is 4, 1, just to keep it simple. I can also deal with non-symmetric matrices, but let me just keep it symmetric for now. And so what I'd like to do is assign all of these rows of the matrix to different processors, or I want to assign different vertices of this graph to different processors. So let me just talk about how I would do that. And so here is here's one way to partition the graph, and I claim it corresponds to partitioning the matrix. So in this case, I have 3 processors, and each one has gotten a subset of 2 vertices. Okay? And so now the question is, how does this correspond to over here? So one processor owns rows 1 and 2. It's a processor that owns vertices 1 and 2, and so forth. So now that's load balanced to perhaps. It's balanced the number of rows right now. So let me look at the edges and see what happens there. So this orange 1, that's 2, 3, that corresponds to that edge from that processor to that processor between vertices 2 and 3. And that green one, that corresponds to that edge connecting those 2 processors between 1 and 4, and so forth. And so this is what I'd like to do is choose this partition so that I minimize the number of edge crossings. That means minimizing the number of non-zeros that are not in the diagonal blocks. Right? That's the same problem. I want to remember the graph partitioning was have as few edges crossing from one processor to another, and here it's have as arrange the partitioning so I have as few non-zeros out here as possible. So it's exactly the same problem that I had before, and we'll use the same tools to solve it. Okay, so to summarize, what are the common problems here? I have load balancing, and that turned into a graph partitioning problem that came up in both discrete systems and sparse matrix-vector multiply. And it's going to be expensive, so hopefully I'm going to do lots of sparse matrix-vector multiplies because the solution costs a bit. But I may have to do it once in a while if the load changes significantly during the job, if my structure changes for some reason. We've seen linear algebra come up a whole bunch of times, solving linear systems of equations, mostly sparse, but we've seen dense ones before too, and they're eigenvalue problems. And we've seen these fast particle methods. So the fact that I can actually compute all the far field forces not in n squared time, but in order n log n. So I've written these down here because I want to remind you of an old slide that I've had, I think, in the first lecture, that these are patterns that come up over and over again. And so just to remind you of this very complicated slide that we had once before, I claimed that there were 7 computational patterns that came up over and over again in high-performance computing. They were operations on, and each of these red bins represents them. So if you do high-performance computing, you're going to do a lot of work with dense matrices, with sparse matrices, with FFTs, we've just seen all of those, and also with n-body codes. So now we've seen them with particle methods, and then the embarrassingly parallel stuff. So let me just circle those. Those are the ones I've just illustrated show up in either discrete event systems or particle methods or lumped systems. And the rest of this picture was saying that they come up in all these other applications as well. So, but there's still 2 missing, structured grids and unstructured grids. But they're about to come up when I do the final sources example, which is where everything is continuous, which is partial differential equations. So are there any questions before I go on to partial differential equations? Okay. Okay. So I don't think I need to do this recap since I'm in the middle of it all. I'll just say that what are our common goals? Load balancing, locality, and the fact that there are going to be trade-offs between these two. Okay, so let me just go on now to partial differential equations. So what are the canonical examples that are going to come up? They sort of fall into 3 categories, and they're going to have their own patterns of parallelization. So there's problems which are called elliptic. That's gravity and electrostatics. In that case, you have some sort of steady state that you want to compute, but everybody depends on everybody. So there's a global space dependence. And so the output is going to be some scalar function as a function of position, where everybody depends on everybody. And so that's one flavor. The next one is going to be actually easier to parallelize. Those are wave equations. They happen to be called hyperbolic differential equations. So they depend on time, but it only depends on your nearest neighbors, so to speak. Why is that? Because waves don't move infinitely fast, right? They move at the speed of sound or the speed of vibration. And so that's going to limit how many of your neighbors you have to talk to, and so there's not going to be that much communication. And so those are going to be easier. And then the last category happen to be called parabolic equations. Those are time dependent, so they will change, but they have this unfortunate global space dependence. Everybody depends on everybody. So where does it, I mean, that violates relativity, but nonetheless, this is the standard model for how you model heat flow or diffusion, right? These are classical equations. And so these are going to be, maybe, since they're the hardest, I will use this as an example. I'll just show you a very simple example of solving the heat equation to say how that works. And so when I have the words here global and I have local, global is bad. That means I'm either going to need a lot of communication or very tiny time steps or very clever algorithms to minimize the communication. And local, that's good. Finite wave speeds, I don't need to communicate very much. And of course, in the real world, these are model problems. The real world with Navier-Stokes or elasticity, they're combinations of all these. So you may have to have all of these in your simulation. But let me just do the simplest one, just to show you what the ideas of parallelism are. And so we can blame Fourier for this. He wrote it down first. It's the heat equation. And so I have an iron bar here that's red hot, glowing red hot at one end, and it's ice cold blue at the other end. And I'd like to know what's the temperature in between as it changes in time. And so what I'm going to do is write down the equation and use that as a model to talk about parallelization. And so I'm going to let u be the temperature, and it's going to depend on the position from 0 to 1, that's x, and the time. So I know the temperature at the beginning, and time will march forward, and I want to know how the temperature changes. And what Fourier wrote down, he said, well, how fast does the temperature change? What's its rate of change at a particular point? It depends on the difference between the gradient, temperature gradient a little bit to my right, and the temperature gradient a little bit to my left. So suppose the temperatures are -1, 0, and 1. So there, the gradient is 1. There, the gradient is 1. That tells me I'm not going to change at all. I'm going to be stuck at 0. But suppose the temperature goes from 1, 0, 1. Both my neighbors are hotter. I'm going to go up, right? So how do you capture that simple physical intuition? You take the temperature gradient a little bit to this side. So that's the temperature at x minus h minus the temperature there. And I take the temperature gradient to that side, I subtract, and I divide by h. That tells me how much the gradient changes from side to side. It's calculus. You let h go to 0. This is the heat equation. So that is the second derivative of the temperature with respect to x. So it just captures that physical intuition. So that's what we need to solve. And how am I going to discretize it? I mean, this is pretty much the discretization. But let me just start from this point and write down some different ways of solving it. So there's the heat equation again. And there's some constant that depends on the conductivity. So what I'm going to do is start with the explicit method, so analogous to what we did with the ODE. And so I'm going to use an equation, forward Euler, to approximate the time derivative. So I'm going to say, well, what is the derivative with respect to time? It's going to be the temperature a little bit forward in time, so not at t, t is now, t plus delta, minus the temperature now divided by delta. So that, when delta is small, that approximates that. And there, that expression is exactly what was on the previous page before I let h go to 0. So what do I know? I know the temperature at time t, and I know it to my left, I know it to my right. So all I need to do is solve this equation for the new temperature at time t plus delta. So I just simplified that a little bit, collected some terms, and I'm going to solve for the new temperature. And it's this nice, simple linear combination. So these are all the temperatures right now, right where I am at position x, a little bit to my left, a little bit to my right. So all I have to do is take a linear combination of a few numbers and update it to get the next time step. That is a matrix vector multiply. In fact, it's a sparse matrix vector multiply because it only depends on 3 values in the vector. And so let me just write it down a little bit more simply. This is a constant. Let me just give it a name. I'll call that constant z. And so there it is. I take a constant times my neighbor to my left, a constant times myself, a constant times my neighbor to my right, and that gives me the new variable. So I'm only going to do this at discrete time steps. So just as I did for solving the ordinary differential equation, I only care about x at discrete points, so h, 2h, 3h, and 4h. So I'll just change the value variable x to be evaluated at j times h. J is an integer. I only want the values at times t equals delta, 2 delta, 3 delta. So I'll let I tell me how many time steps I've taken. And my continuous function will be replaced by this 2-dimensional array. The first subscript tells me the x. The second subscript tells me the y. And so the inner loop is going to do this update. at position x, time I plus 1, I take this linear combination of three numbers, and that gives me the new value. That's the explicit method for solving the heat equation. It's not a good idea, but it's our first approximation. And so here I've drawn the whole two-dimensional array just to make it clear what we're doing. So I'm going to start by, I know the temperature times 0. So there's my iron bar going from left to right. I know the temperature when I get started. I have to know a little bit more information to solve it for it to be physically well determined. I have to know not just how it starts, but I have to know how hot is the left end of the bar and how hot is the right end of the bar, right? Because they could be at different temperatures and things will change. And so I'm given some boundary information, the beginning data and the temperature at the left, the temperature at the right, the temperature at the left. And now I know enough to evaluate this, and I can step forward in time over and over again. Starting at the bottom, I compute these values, then those values, and those values. And everybody depends on their three nearest neighbors at the previous time step. So those red arrows indicate that to compute him, I just need to know three values from the previous time step. That is going to be expressed on the next slide as a matrix vector multiply. I'm going to take the vector of those values at time I, multiply them by a sparse matrix, and get the vector of values at time I plus 1. So let me just write down that matrix and then think about what it looks like. So I've just written down that equation again, and I'm saying let's recognize I'm doing a sparse matrix vector multiply. So this is the vector of all the temperatures for all the positions at time I plus 1, time I, multiplied by the sparse matrix T, which I've written here. It's tridiagonal. That's because I only depend on my own value and my left neighbor and my right neighbor. That makes it a tridiagonal matrix. And it has a lot of common properties, so there's a 1 down the diagonal, so let me pull out that identity matrix. And then everything else has a z factor. Let me pull out the z factor. And so all that's left in each row is 1, minus 2, 1, minus 1. Looks like that. That is a famous matrix. It's called the Laplacian. It's going to come up over and over again in gravity and everywhere else. So let me just give it a name L for now. And the other thing to notice about it is that it really is very simple, right? I mean, it's the same number down each diagonal. So I don't actually have to store it explicitly. All I have to do is know there's a 2 on the diagonal and minus 1's in the off diagonal. So this picture captures it all. And often when we have a matrix like this, we call it a stencil because it's the same pattern at every mesh point. And so it says that for every mesh point, I multiply my value by 1 minus 2z, z by the neighbors, and then I add them all up. And so this is called the Laplacian in 1 dimension. And eventually I will draw the same thing because we want it in 2 dimensions and in 3 dimensions. And so in the 2-dimensional case, I depend not just on my neighbors to my left and my right, it's also above me and below me, right? So how many non-zeros are there going to be in each row of the matrix? I have 4 neighbors, top, bottom, left, right, plus myself, so there are going to be 5 points. So it's going to be a 5-point stencil, and I'm going to have 5 diagonals in the matrix. And so that's what I need to do to do a sparse matrix vector multiply by that very special matrix. So let's ask, what's the parallelism here? And if I were to use the techniques that I talked about before, I would say, okay, I have this nice simple matrix. I want to do graph partitioning. Here I've drawn the graph that corresponds to the matrix. There's 1 vertex for every row, and I'm only connected to my nearest neighbors. It's a tridiagonal matrix. So this is the simplest possible graph you could imagine to try to partition. I just break it up into adjacent chunks, and there's only 1 edge connecting 1 chunk to the neighbor. And so life is good. This is very simple. And so let me just try that. And so let me just do a simulation. I'm going to solve the heat equation. I'm going to use the method that I just showed you. And this is called the explicit method. Each update is going to be a sparse matrix vector multiply. And you'll see on the next slide that it's actually a very bad numerical method. It's going to blow up. So even though I did all the calculus right and I showed you that, if I try to take a time step that's not incredibly tiny, the solution is going to make no physical sense whatsoever. So if I just back up here, this number z, which shows up in the matrix, it turns out that it's only going to work if z is less than 1/2. So is that a very big constraint? I'll show you a picture in the next slide. Well, remember, what is z? It's constant conductivity times the time step divided by the spacing on the mesh squared. So suppose I want to make my mesh smaller to make it more and more accurate. Suppose I want to divide h by 10, so have 10 times as many mesh points. What happens to my time step? it goes down by a factor of 100, right? So I have to have very, very tiny time steps for this to be stable. So let me just solve it and see what happens. So I'm going to solve it once when z is a little bit less than a half and everything works fine. And I'm going to try solving it when z is just a tiny bit bigger than a half, just to see what happens. And so here is a picture of the numerical solution. So I have an iron bar, and the iron bar goes from that side to that side. The vertical coordinate is the temperature, and so it's ice cold on both ends. It's really hot in the middle. I'm going to say what happens to the temperature in the iron bar. Well, if I start with a hot iron bar and the ends are cold, it's going to cool off, right? So that's what this picture says. Time is marching forward, so that axis is time, this axis is temperature, and that axis from left to right goes along the bar. And so eventually, the middle of the bar cools off, and it goes down to 0, as I expect. So that's with taking it z, that little step, just less than a half. Now, what if I make it just bigger than a half? It decreases for a while, and then it starts going crazy and oscillating. And this makes no physical sense whatsoever, right? I have negative temperatures. You're going to get as large as you like. And so that's why this explicit method is not so popular for solving parabolic equations. It's popular for some other methods like wave equations. It's fine. So I need to do something implicit. So let me just show you what different parallelization problem that turns into. And it's analogous to what I did for the ODE case. I'm going to use not forward Euler. I'm not going to approximate the derivative at my current time step. I'm going to approximate it at the next time step. And instead of doing a sparse matrix vector multiply, I will get a system of sparse linear equations to solve. But let me just write it down. So here is how I approximate the derivative with respect to time. That's the same one I had before. There's the approximation of the second derivative, and the only difference between the previous one and the new one is that I used to have a t there. This used to be at the current time step. But now I'm approximating that second derivative at time t plus delta, the new time step that I don't know yet. So what I need to do is solve this for the next time step. And so let me put all the stuff that I don't know, that's the time step t plus delta on that side. That's what I do know, that's my current temperature. I will again, simplify it. I'm going to, let z be the same constant that I had before. I'm going to only be interested at time steps delta 2 delta 3 delta, only at positions h2 h3h. And I'm going to change my continuous function to the square array. And so I know my values at time I. I want to get them at time I plus 1. How do I do that? I have to solve a system of linear equations. So that vector is all the temperatures at time I. That vector is all the temperatures I don't know at time I plus 1. And there's the sparse matrix out front that I have to solve. Identity plus that constant times the Laplacian. So I still have, so now the Laplacian comes up again, but it shows up as a coefficient matrix, and where I have to solve the system of linear equations. Okay? So this solving equations with Laplacian comes up all over the place. This is the simplest example. Now, in one dimension, this is really easy, right? It's a tridiagonal system. It costs me order n. This isn't a hard problem to parallelize. It's when we do it in 2 dimensions and 3 dimensions it gets interesting. So here, just so you know, that I'm just repeating what I had in the previous slide. To get from time step I to I plus 1, I solve a system of linear equations. That was a motivating example. People don't actually do that in practice. They use something just ever slightly more complicated called the trapezoidal rule. And so there's a sparse matrix vector multiply and a solve in it, right? So you got to do both, right? So you take a half a step with the sparse matrix vector multiply. The Laplacian is still there, and but you still have to do a solve. So this is what people would actually do. So both problems come up. And so again, I have to solve an equation with a Laplacian in it. And sometimes people solve just Laplacian times x equals b. That would be, for example, Poisson's equation. So that's what electrostatics and gravity need to satisfy. They're going to satisfy not this one, that's for heat. We're going to solve this equation instead, the same L times x equals b. So just to remind you, again, this is a very high-level tour to motivate a bunch of parallel computing we're going to do later. So why does Poisson's equation, Laplacian times x equal b, come up in gravity and electrostatics? So here's one slide to remind you of that physics. So I want to compute the force on a particle at x, y, z. It's living in 3-dimensional space. Due to a particle at 0, they're attracting one another. So inverse square law. The force in that particle is a vector that's pointing from the particle back to the origin. So it's minus x, y, z. And I'm dividing by the length cubed, so it's an inverse square law. So how do we really solve that in practice? Well, what you notice from a physics class is the force is the gradient of a scalar function called a potential. So this is proportional to 1 over r squared. The potential is just a scalar function minus 1 over r. And here I've drawn a surface plot of what minus 1 over r looks like. So it blows up to minus infinity near 0, and then it gets smaller as r gets bigger. And it turns out that these forces here, if you go and compute them, it just is the gradient of this potential. So if I just compute that one nice simple scalar function and differentiate it, it'll tell me the forces. And that is Poisson's equation. And so if I can solve for that potential and then just differentiate it, I get what I want. So that's where Poisson's equation, or the Laplacian, comes up. And so let me just show you what it looks like in 2 dimensions. This has all been one-dimensional so far. So here's what the matrix looks like in the 2-dimensional case. I'm still going to have, a constant down the diagonal. It went from 2 to 4. I still depend on my nearest neighbor on the left and the right. So I still have those minus 1s. So here's the nearest neighbor on the left, the nearest neighbor on the right, but I also depend on the ones right above me and right below me, so I have 2 more minus 1s that are farther away. Because how have I built this matrix? Well, I've numbered the points in the stencil from left to right and then top to bottom. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And so this guy here is that guy, and these 4 minus 1s are those 4 minus 1s. And I could draw the 3-dimensional case too. In that case, I'd have 7 minus 1s. Excuse me, 6 minus 1s, and then another number on the constant. So I need to both solve systems of equations with this guy and do matrix vector multiply. So now let me give you a 1-slide summary of all the methods people have tried over time to solve this particular system of linear equations and what their pros and cons are from a parallelism point of view. And I'm going to structure this as a conversation. I often have this conversation in my office hours. Somebody comes in to my office hours and says, I need to solve AX equal B. And that's all they tell me. And I say, OK, great. There's this algorithm. It's called dense Gaussian elimination. It'll cost you n-cubed operations, where n is the size of your matrix, and that's all you need. They write. And they say, no, that's not fast enough. I say, well, tell me something about your matrix. And by the time we go through the conversation, we've gone through all of these different algorithms until we get to the fastest one at the bottom. So I've sorted these in order from the most general but slowest method in order of how fast they run on the Poisson equation. Each algorithm uses a different mathematical property that is the Poisson equation has, and depending on your problem, you may get down only to the middle of this because your problem may only have some of the properties of Poisson. But if you get all the way down to the bottom, well, you're going to be optimal. So the next thing they may tell me is that, well, all right, my matrix has a lot of zeros in it. In fact, if you go a little ways away from the diagonal, let me just go here. If you go far enough away from the diagonal, it's all 0. I said, oh, you should have told me that. That's called a band matrix. And then they tell me how wide is a band. And I say, oh, OK, there's a standard algorithm for that. It's called band Gaussian elimination. And the complexity is going to go down from n cubed to n squared. You should be very happy. And they say, still not good enough. OK, tell me a little bit more about your matrix. Then they tell me, well, I'm going to be solving it over and over again for lots of different right-hand sides. So can I do something better there? And I say, well, not really. Because if I were to take your matrix and invert it once and make an explicit inverse, it would be dense. So it would be an n by n dense matrix. You could do a matrix vector multiply to do it, but it still costs you n squared at every step. So that's not going to help. So tell me some more about your matrix. And they say, well, actually, there are only 4 non-zeros in every row, 5 non-zeros in every row. And I forgot to tell you it's symmetric. And I forgot to tell you that it's actually, all its eigenvalues are in some reasonable range. They're all positive. I said, oh, you should have told me that. There's this other algorithm called the conjugate gradient method. It just does sparse matrix vector multiplies in the inner loop. And your complexity is going to go down all the way to the end of the 3 halves. And they say, it's still not good enough. I say, what are you really trying to do? And they say, oh, I'm trying to solve the heat equation, right? So why didn't you tell me that? You should use the FFT or multigrid. That'll get your complexity down to n log n or order n. And n is a lower bound. You're never going to go faster than that, right? You've got to do at least one floating point operation per answer, component of the answer. So what I've done here is sort of recorded, we're going to do several, not all of these algorithms over the course of the semester. Each one of them uses more and more properties of your problem. So you should exploit as much mathematical property that your problem has, because you want to go as fast as possible. I've shown you what the serial complexity is, both for the two-dimensional Poisson equation in black and the three-dimensional Poisson equation in red, because sometimes that scales a little bit differently. I've shown you what the complexity is for this artificial parallel computer called a PRAM, where you can have as many parallel processors as you want, and communication is free, so it's kind of like, imaginary, but it tells you how fast you can possibly speed it up. I tell you how much memory it uses, that gets better too, and how many processors you could possibly use, if you had all the processors in the world. And so for the Poisson equation, this is a nice, simple linear ordering. But of course, not every problem fits in this nice linear ordering. So what people have tried to do is actually build a decision tree, so that depending on what properties your problem has, there's sort of this sequence of questions that will lead you down different branches in this decision tree and finally say, choose this algorithm, right, depending on which properties you have. And so there's a pointer to this online book where we've tried to build this decision tree. So, but all of these are going to come up, and we'll talk about a subset of them over the course of the semester and how they parallelize. Okay, and this slide just summarizes the kind of tour that I gave verbally on that. So, okay, so let me just say a few more words about the algorithms, because there's two metrics of success that you might have in your mind for an algorithm, which is what is the total runtime and what is the speed? How many floating point operations per second does it do? And which one do you think is more important? The total runtime, obviously, right? You just want to know how long do I have to wait for it to finish. And so here's some data just to show you that you can get two completely different answers depending on your metric of success. So this is really old data, you can tell, but it's a reasonably large machine, 1,000 processor machine. And what they did is they took 3 algorithms from that list that I gave you. They're all iterative methods, Jacobi, Gauss, Seidel, and multigrid. And they implemented them to solve the Poisson equation. And what I have here are 3 measures. How many total number of floating point operations that they took to solve the problem, how much time they took, and how fast the algorithm actually ran. And so Jacobi ran the fastest in the sense that it did 1,800 megaflops per second. That was a lot back in 1991. And multigrid ran 6 times slower. On the other hand, it took 300 times less time to converge, right? So obviously, this is what you care about. It's not the fact that it's hard to get the inner loop of multigrid to run that much faster. So anyway, this is kind of an obvious comparison. I just wanted to make sure that you knew that what our metrics of success were. Okay, so just to summarize these different approaches here, so you have both explicit methods and implicit methods. In the explicit case, we're going to spend all our time doing sparse matrix-vector multiply. And there are some partial differential equations, like wave equations, where that's exactly what you want to do. And sometimes that's used as a building block to do the next one, which is implicit. But implicit is intrinsically more expensive. You have to solve a big sparse system of linear equations at every step. There are 2 ways we're going to talk about doing that in later lectures. Direct solvers. The FFT is one example, which is very finely tuned to Poisson, or for more general sparse systems. Or there's these iterative ones. And making both of them fast is going to turn into a graph partitioning problem. So let me now just give you a little eye candy of what real meshes look like. And because I've only shown you 1D and 2D and 3D meshes, but real meshes are often very irregular. So I just want to show you what it looks like and what are the other problems. So how do we get real meshes in the world? Well, we can take a bunch of regular ones and glue them together to get sort of composite meshes. I can also have like totally unstructured meshes. You're doing a finite element model of some arbitrary widget that's going to be irregular. And people also often have adaptive meshes, because the physics is going to change. You have some flame front going through a material that you're simulating, and you have to change the mesh as the flame front moves. So here is the picture we've seen before, which is, I just have these ghost zones. I talk to my nearest neighbors. But let me show you what happens with a real mesh. Let me try to now use this as a building block for a bridge abutment, right? So it might look like this. And so here is a perfectly regular rectangular mesh. Each of these bricks is. But I've glued them together at the end so that I can have this more general structure. So the question is, what does this look like if I write it down as a matrix? What kind of structure does it look like? So what I'm going to do is number the nodes. I'm going to say, oh, that's a nice regular thing. I'm going to number it row-wise there. That's going to be nodes 1 through 49. Then I'm going to number those, number those, number those. And those gives me all those band matrices down the diagonal. So that green band matrix is that guy. That's the same structure as Poisson. That blue one there is that guy. But of course, that's not all I have because they're all connected in these irregular ways. All these red edges are connecting them, and those gives me all those red dots that are farther away from the diagonal. Those are going to mess things up. So let me just try now to go ahead and do Gaussian elimination just for instance, to show you what happens here. So there's a picture of the matrix again. All the black dots are the original non-zeros. And if I actually try to solve that by doing Gaussian elimination, taking into account the fact that it's symmetric, it's called Cholesky, then I get a whole bunch more work to do. But I also fill in a lot of the entries of the matrix, because when I add a multiple of one row to the next row to do the elimination, I may create a non-zero where it wasn't there before. And so all the red dots are all the new non-zeros that I created. And this is going to cost me, for this relatively small matrix, about 300,000 operations and about 11,000 rows. So let me now, just to motivate a later lecture, say I don't have to do the matrix exactly the way it was given. I could have reordered the rows and columns. And so here is an algorithm where these two matrices are the same. The only difference is how I've ordered the rows and columns. This is kind of a funny graph algorithm that we'll talk about later. So what happens now when I do Gaussian elimination? It still fills in, but I only get the red stuff. So I get a fraction of the number of non-zeros, and I also get a fraction of the number of floating point operations. So how did I decide that was the right order? Well, that's going to be a later lecture. So that's one method. Let me just show you a few more pictures here. I know it's late. So here, this example is built into MATLAB. You can look for it under airfoil. So this is a very irregular mesh because I want to have finer resolution where the mesh points are near the boundary so I can know exactly what's going on there. There's what the matrix looks like, and there's what happens when you do a solve. It fills in that way. And the question is, what's the best way to order it? We can also get irregular meshes by starting with something that looks like this and saying, I need to approximate that, so I'm going to take every other mesh point and use that as an approximation. So this is the same graph, or the same matrix, but I've just taken out every other mesh point. That is the same one as that, taking every other mesh point. And that mess is allegedly that one where I've taken every other mesh point and is used as an approximation. So I generate all those. And let me show you one real biomedical example. And so this actually turned into a startup. And so here's the motivation, which is that old people have osteoporosis. You want to know how to treat them. And so you'd like to know how likely are they to break a bone when they fall. And so what the right thing to do is to do a finite element model of their bones and ask how likely are they to break if there's under particular stress. So here's a real bone taken out of a cadaver. And so here is the kind of analysis people did on this. They didn't, the real medical process on real patients does not require taking out their vertebrae, but this is the science that was done first. So that bone was taken out. It was put into a micro CT scanner, and in a very accurate 22 micron resolution was taken of exactly where all the bones and all the air was. I mean, bone is mostly air, right? And so that's what it looks like at 22 micron resolution. Then there was a finite element model built, and so there are all the little meshes that go with that. And that turned into a 500 million by 500 million matrix that they needed to solve to ask, what is the likelihood that if you put a certain force on this, it will break. And so this won the Gordon Bell Prize back in 2004, and it turned into a startup. And of course, they can't afford to do this high resolution, high radiation imagery on a living patient, so it's done at lower resolution. But this proved that they could reproduce the values in the laboratory because they actually smashed the vertebrae, and this predicted exactly when it would break. So I'm almost done. Here's another picture of where real meshes come from. This is a supernova exploding. And as the front moves out, you have to move the mesh along with it so that where the actual chemistry and interesting physics is happening, you get a finer and finer mesh. And there have been several systems built to do this for you, so you don't have to do this by hand. And we may have a guest lecture later on what these look like. And so let me just, all right, so one more picture in this adaptive mesh refinement. And so what are the challenges? How do we generate them in the first place? So you start with a geometric description of the object, and then there's a bunch of interesting software tools that have been built already that will actually generate the mesh from your high-level geometric description. You have to partition it. There's a lot of software that's already been written to do the graph partitioning. We will talk about Parmetis and other systems later in the semester. Then there's building all the iterative solvers. There's a bunch of systems that have already been built to make it easy to write, to express all these algorithms. And anyway, so there's just lots more to do, and this is just a tour of that's motivating much of the rest of the semester. Okay, I'll stop here.